My name is Leonardo, if you prefer, and I will be talking a little bit about SQL queries and what happens inside the database when you actually run a query. What do I know about that? Before becoming a developer here in Canada, I used to work for the past 12 years as a database administrator. So I'm somewhat quite used to optimize and write queries and understand what's happened when you actually run a query. And that's what I will be talking about here today. So first, what are the topics? A little introduction on what is a query, what happens on the processing of your query, what is an index, a quick overview because there is a lot about indexes, what is it, execution costs, what are execution plans, and statistics. So without further ado, what's a query? A query is a SQL instruction that retrieves data based on specific criteria. And one point important about the queries is that it's in a declarative form. So it's not like most of languages that are imperative, that you actually say what do you want to be done. In a query, like on these examples, you say what data do you want, but you don't say to the database how it's gonna read the data, how it's gonna return the data. You only say what do you want, which data do you want. And your queries can be as simple, like the first one, select asterisk from users, or as complicated as the second one, that is still quite simple, that it's just for representation. There's a join, there's a word, there is having, group by, order by, yada yada. So what happens when you actually hit enter in your query or when your application sends the query to the database? It depends on the technology and which product are you using for databases. Here specifically, it's the parsing structure for Oracle databases. But the Postgres database, it's not that different. And on MySQL, it's not that different either. So first thing, your SQL statement enters to the parsing process that does syntax check to see if you didn't write form instead of from, or select instead of select, and things like that. And also a semantics check. It verifies if your query, besides being all syntactically corrected, if it makes sense, if you are actually asking for a table that exists, if you are asking for a field that exists in a table, and things like that. After that, it actually checks if this query was already run and if there is already a plan for this query. I will talk about plans in a few minutes. But if there is a plan for this query, the database will not do that again. So it's going to do something that's called soft parse and goes straight to the execution. But if this query were never run or it was run in a long time ago, probably this query will not be on the shared pool of queries. So then you will have to pass through a hard parser. That is the most interesting part on that. That is the optimization. And what is the optimization? It's the database finding the best way to read the request data. And for that, it uses several tools and several methods like query transformation. It actually change your query to make it more efficient. We're going to see a small example of that. Access paths. Well, how am I going to access the data? I'm going to go to the table A first and then to the table B. I'm going to use an index or not, and things like that. I'm going to check the indexes, what indexes exist, and how good are they for my query. And also, I'm going to check the database statistics. And for some databases, Postgres is not the case. Postgres don't have that. But for some databases, also it's going to use hints that are defined by the developer in the query to force the database to use a specific way to resolve that query. So hints, as I said here, it's not available on all databases. So just a few details about query transformations. As I said before, the optimizer changes the query structure to make it more efficient. Modifies things like join order, Boolean operators, and so on. So sometimes you do a bunch of ORs, and the database, to make it more efficient, transforms it to an AND, or even the opposite. Gets a bunch of ANDs, it transforms it into ORs or XORs, make it the most efficient way to solve your Boolean query. And also, not all databases does that, and not all databases does it the same way. So each database knows their better way to solve a query and makes these transformations the better way for them. Access paths. As I said before, evaluates the possible access paths to the request data, like indexes, like tables, like blocks in memory, and things like that. I talked a lot about indexes. What are they? Indexes are storage structure for parts of data to improve access time to records. Most of the time contains one or a few of the table columns. And usually it's ignored. It's just like it's not there when you do have a small data set. So if your table is too small, your index will be ignored. Or when your query reads large percentage of your table data. So if you have a query who reads more data, depending on the database, but for Postgres, if it reads more than 45% of your table data, the Postgres will actually prefer to read the entire table instead of actually using an index. And most common data structure for indexes, it's B-tree. It's a balanced tree. It's not the only one. Each product has its own set of data structures that support it for index. Oracle and Microsoft also have tables that are index structured, but the most used one is B-tree. And this figure here represents what a B-tree is. So it's actually a tree. So I have a root node, and in this, it's not a node, sorry, it's a block. So in this block, I do have a whole bunch of intervals and addresses to another blocks. And so here I do have an interval from 0 to 40, go to this block. So there is an address to this block inside the index. And then here, I do have intervals of that interval that points to another blocks. And when I reach on the leaf blocks that are mostly 4 levels down, tops, I do reach in a point that has the value and a row ID, that it's an address to the actual data in the table space. So actually, this row ID, it's the address of your record inside your table, inside your database. So let's say, for instance, that I want to read all zeros that are on my database. All IDs equal 0 or salary equals 0 or whatever. So I'm going to come to the index. I'm going to read, in this example, 3 blocks. And I will have the address of all blocks that are actually 0 on my table. Without an index, I will have to read the entire table to find the blocks, to find the records who have 0 on that field, to actually be able to process as the user asked. No. Another information that I used before, that I talked before, and that is used to actually define the way that the database will be resolving your query, is the cost. And cost is actually an abstract value that the database calculates, and it's different for each database solution, that it's an estimated measure on how hard it is to actually read the data. So based in things like memory usage, for some databases, memory speed, CPU usage, and I/O. And as it is estimated, the numbers may vary between databases, and also, even depending on the structure that you made in your database, for the same solution you can have different costs for the same table. And also statistics. It's used to evaluate how many records the query will actually manipulate. They have two basic measures. Actually, most of the time you have much more measurements than these two, but the most basic are selectivity and cardinality. Cardinality is how many records there are on the table. And selectivity is for each different value that you have on the table, how many records do you have there? So for instance, how many Andrews do I have in my employees table? So the selectivity, it's going to be the number of Andrews divided by the total number of employees. So this way I know how is the percentage of records that I will have to read from the database when I do a query. Generally, it's automatically collected by database processes, but you can also run it manually. So most of the databases, when you finish installing it, it creates a daemon job weekly or 2 or 3 days once in a while that actually collects these statistics and stores that in your database ready for you to use, and you don't actually have to do anything for that. They are just there for you. But if you do a huge change in a table, maybe to actually make your query run properly, you will have to manually collect the statistics, because you did a change on Monday and your statistics will only be collected on next Sunday, for instance. So the execution plan itself, it's based on cost and statistics. Your database instance defines some execution plans, some ways to actually read your data. And the lowest overall cost is usually elected and used. So your database starts calculating 2, 3, sometimes even 10, 20 different execution plans to actually execute your query. And for each of those queries, you do have a calculated cost based on the cost and the statistics. And then when it does that, it quickly chooses the better cost, the smallest cost, and uses this query. And then this selected plan is cached and reused if necessary. So if you run this query again, it will not actually create a new execution plan. It goes straight to this plan as we saw before on the soft parse. But be aware, the select plan is not always the best plan. Sometimes, because of the statistics or because of the kind of indexes that you have, because of the cost and the statistics are actually an approximation of the data that you actually have, because your table is changing all the time, sometimes the plan is not actually a good plan. So let's see some examples. So here, I do have a table without any indexes that has ID, has employees with IDs cardinal from 1 to 100,000. So I did a select everything from T where ID is less than 10,000. So I'm taking 10% of my table, and I don't have an index here. This explain analyze in the front does two things. The explain actually shows an execution plan, and the analyze, this is for actually Postgres. And the analyze actually runs the query and shows you the actual time to run this query. So here, what happened? I do have a sec scan. That means I'm reading the entire table and I'm filtering rows. So remove it by filter. 90,001 rows. The planning time to generate this plan, my database took 44 millionesimes of milliseconds. I don't know how to say this, but the execution time was around 8 milliseconds. These 5 rows is just the number of rows in this plan. And here, 2 informations are interesting. The cost here is the starting cost of this step and the end cost of this step. This number doesn't say anything by itself. How many rows it's estimated to read, and what's the mean width of the data. And actually, where's my mouse? Here it is. No, I lost my mouse again. This is the actual time. You see, because of stale statistics, it estimated that was going to read 94, 90, and 40, 9,940, and actually read 9999. And this was actually the time spent processing the data. Okay? Then here, I actually created an index on this table and run the same query. As you can see, the time fell from 8 milliseconds to actually 2 milliseconds, the execution. But the planning time increased because now I do have one more thing to consider. I do have an index there. So I do have the index and the statistics over the index. So now I do have an index scan using this index, and the cost in the initial cost was .29 because it had to actually access this index, and the final cost on the index was 300 comparing with 1600. So it was a lower cost. That's why it shows that plan was still there. The database could use that plan because it works, but this plan was better. So same statistics for the rows, and actually the execution time with the same rows and same loops. So you can see that an index improved a lot of the time of execution here. But that's not always the case. For instance, here, I do have another query. I'm looking for the latest employee. I'm assuming that my employees were hired, and every time I hire an employee, I increase the ID of the employee. So I'm looking for the latest female employee that was hired. What was its ID? So select max ID from T where gender equals F. So the plan, without any index, I'm going to do a complete scan on the table, same cost as before, and then I'm going to aggregate to pick up the biggest ID. So plan, low time to executing plan, and the execution time was around 16 milliseconds, sorry. And if you take a look here, this is the same time. I do have the times here. How many rows in my 100,000 rows in my table I do have that are females? That are around 50%. And then I created actually an index for that. This is a type of index that are specific for binary data. So if I have a kind of data that are usually in discrete and a small number of variations, I can use this kind of index. And I can see here the plan. It's actually using the index. The cost, it's a little bit lower. You see 1,800 versus 1,500. So it's a little bit lower. But the actual time was worse. 15 milliseconds against 17 milliseconds. So in this case, using this index, the query was worse. The execution of the query got worse. So this is an example that it's not just throw there a query and it's going to improve. Not always. But I was looking for gender. That was my search. And then I created an index on the ID. The same index that I created before, I created it again. And actually, the execution time improved a lot. Why? Because the database actually transformed my query, and instead of actually looking for gender, it actually started looking backwards for the ID. So it went straight to the index, to the biggest IDs, and then from there started looking for the first female that it could find. And then, because of that, my actual time was really lower. But you can see here that the possible time, the possible cost was actually really higher than was expected. This is because of the worst case scenario. When it evaluated just the max ID, this was the worst case scenario. Well, that's it. Any questions? Actually, you don't. Usually, the most used scenario is actually you are going to verify if there is already an index in the field that you are querying. And after that, if there is, you are actually look the execution plan to see if the database is actually using that index. Before I didn't put it here, but I created a B3 index on the same field. And because of the size of the table, and because of the amount of data that was being read, the database was simply ignoring the index. So if I create a common index there in a field that has just 2 values, and 50% of the values are the same, it's going to be cheaper for the database to actually read the entire table than to actually read half of an index, and then grab those IDs and go to the table to grab half of the table. But it comes first. Take a look in your join conditions and your selection conditions, or the where and the join, and see if you do have indexes on that. And take a look on your selectivity and cardinality. If you are taking too much data from the table, you maybe shouldn't use an index or should use a different type of index. Okay? Okay.
Okay, so in your latest example, so there was 100,000 rows, I'm guessing, in the table?
Yeah, 100,000.
Okay. So the way, so the one where there was no index on the ID, you were saying basically, this is my understanding of it, the search time for finding the optimal route plus the searching over n over 2, n being 100,000 for your example.
Sorry, I got lost.
Over the 50,000 rows by
yes.
just doing the gender filter first and not indexing on the ID.
Yes.
That is slower than indexing on the entire table, but not having to do as big of a search. Is that kind of
yeah, what I was trying to say was, when you do have data that is binary, like male or female, or even minor or adult and things like that are somewhat binary, the usual index, it's not that effective for that, because the index is it's cheaper to be read, but it's not free. And if I do have to read, for instance, for Oracle databases, the magic number is around 20%. If the amount of data, the selectivity of the field that you are reading, it's bigger than 20%, Oracle database usually prefers to read the entire table.
Okay, it's because there's so few values. It's basically within a constant factor of.
Yeah, exactly. I do have a selectivity too high because the amount of males, it's 50% of the database.
Yeah.
So
You're pretty much scanning the whole thing.
exactly. I'm looking at the statistics, and I know that for this query, I will have to read half of the database, half of the table. So the database makes an assumption that using the index for that, it's losing time, because I will have to read a whole bunch of lifts in an index, 3, 4 levels of index, and then go to the table to read half of the blocks of the table. It's faster if I read the entire table and select from there what I want.
Okay, I have a slight second question. The explain analyze, where is that available?
On every database, you have some form of explain query. Yeah, every database has that. Mongo, MySQL, this one is from Postgres. But for Oracle, for example, it's explain, plan, for, and the query. For MongoDB, it's db.collection.find.analyze. For Postgres, we just saw it. Any more questions? Well, folks, thank you.